So, to talk a little bit more about light as energy, okay, the frequencies of light dictate different kinds of energies. And I say frequency for a reason because as we get to the equation, frequency is what unit-wise helps us out. Okay, so if you want to find the energy of light, the energy is equal to h, which is a constant called Planck's constant. Okay, he's a scientist that studied this and came up with this crazy number, times the frequency of the wave. Okay? Just so you know, some books, and your book as well, traditionally gives this equation as energy equals Planck's constant times this like weird V, because sometimes frequency isn't used as an F. It's as a not a normal looking V, but a kind of like fancy looking one. I'm not going to use that because I feel like it gets confused with velocity, but just in case you see that, be aware of it. Alright, so Planck's constant is 6.626 times 10 to the negative 31st joules times seconds, not per seconds, but time seconds. And this helps us get the unit we want. Okay, frequency is still measured in hertz. And in case you ever don't know your frequency, remember, we're always going to be dealing with light, so you can use your velocity of light equals the wavelength times frequency, and you can always convert back to frequencies. Say you're given wavelength. Okay? So, a couple sample calculations. So, what is the energy associated with a light wave that has a frequency of 4.57 times 10 to the 21st hertz? So, our equation, so energy is Planck's constant times frequency, and if I plug in what I know, Planck's constant is 6.626 times 10 to the negative 31st joules seconds times 4.57 times 10 to the 21st hertz. Sorry, that should have been for SU. When I solve, I get this number, 2.86 times 10 to the negative 12th. And my units, just like we've been dealing with before, if you're not sure on your units, apply the math that's happening. So we have joules times seconds times hertz, but I can write hertz as 1 over seconds, which means my seconds cancel out, leaving me with joules, which we know is the unit for energy. Okay, so this is a very basic calculation. And then just to give you an idea, one that might work out for wavelength, a sodium streetlight gives off a yellow light that has a wavelength of 589 nanometers. What is the energy of the photon of this light? Okay, so for this one, I want to use this equation, but I don't know frequency. So to find frequency, I'm going to use this. Okay, coming from the fact that the speed of light is equal to frequency times wavelength, I know that frequency has to be the speed of light over wavelength. Okay, so I'm going to have 3.0 times 10 to the 8th meters per second over, and then I'm going to do my conversion down here in this. I have 589 nanometers. 1 nanometer is equal to 1 times 10 to the negative 9th meters. Okay, so I play around with my units. Nanometers are canceling, and then I'm dividing meters per second by meters. So those are going to cancel out too. And that's going to give me approximately this number, 5.09 times 10 to the 14th hertz. Okay, because I'm left with 1 over seconds, which are hertz. Now here, because when I plug this in and in the next equation everything is multiplication, I shouldn't actually round here yet. But just so that you can get an idea of what number you should be getting there, don't delete it out of the calculator, because you can take it over here to the other equation And energy is going to be equal to 6.626 times 10 to the negative 34th joule seconds times that number. Okay, and consider it the number that you haven't actually fixed out of the calculator yet. And that's going to give me 3.37 times 10 to the negative 19th. And my units were joule seconds times 1 over seconds. So this 1 over the seconds cancel out again, leaving me with joules. Okay, I know it gets a little complicated when you have more than one equation, but if you just keep track of your numbers and your units, they really aren't that bad. Well, make sure you do the online quiz, and I'll see you in class.